So very good evening to one and all gathered here. So in today's class, we are going to see about the different type of work done equation for various quasi-static process in engineering thermodynamics. In the previous class, we saw about the displacement work done equation. Then we saw about state function and path function. So in continuation with that, today we are going to derive various equation for a different quasi-static process in engineering thermodynamics, say constant pressure process, isothermal process, constant volume process, polytropic process, and adiabatic process. Nearly 5 quasi-static processes are listed out. For each process mechanism, with reference to the PV diagram, pressure volume diagram, we are going to discuss the derivation under each classification. So first, let us start with constant pressure process. So according to the information mentioned in the PV diagram, the constant pressure process can be otherwise termed as isobaric process. So since the pressure is kept constant, as shown in the graph, P1 equal to P2. So pressure is the constant variable, whereas the volume that may be compressed or expanded from the initial to final state depending on the work done. So the next slide, here you can see the work done by the gas is nothing but the constant pressure with respect to the change in volume. So this is the graph rectangular area as per the graphical illustration. So this area covered under the rectangle region, which describes the physical work done by the gas. So therefore, we know that the work done equation W is equal to integral PdV subject to initial volume and final volume. So now we want to integrate this given work done equation according to the constant pressure process. So further equation can be rewritten as, so Pi, that is the constant, that will be brought out of the integral. So Pi is equal to, since constant cannot be integrated, so bring the constant outside, away from the integral. So now the remaining equation will be written as Pi into integral Vi Vf into dV. So we want to integrate only the change in volume dV subject to V1 and V2. So that is initial volume and the final volume. So integral dV can be further rewritten as V power V1 V2. So in place of V, substitute the limit, upper limit and lower limit. So Vf is the final volume of gas and Vi is the initial volume of gas. So Pi into Vf minus Vi. So further, the work done equation can be expressed in short form Pi into delta V, where delta V is the change in volume between the initial and final state. So these are the inferences from the given the constant pressure process based on the PV diagram. So the work done by the gas can be either defined as positive or negative, that depends upon the expansion or compression process. So in this case, PV, that is P into delta V, is greater than 0. The work done is positive because the volume expands from V1 to V2, initial volume to final volume. So work done is positive, it is not negative. Suppose if P into delta V less than or equal to 0, then it is a negative work done. But in this case, it is a positive work done. So expansion process. Next one, constant volume process. Second derivation we are going to see in quasi-static system, thermodynamic system. So here volume is kept constant, whereas the pressure variable is considered to be a differing variable from initial to final pressure. So P1 and P2 are different. It is not a constant, but whereas V1 equal to V2, initial volume equal to final volume, that will be maintained as constant variable. Other one will not be equal to constraint. P1 is not equal to P2 constraint. So constant volume can be otherwise called as an isochoric process. So since the volume is kept constant, there is no work done because we cannot integrate a constant. So zero work done. So work done equal to 0. Next one, isotherm, constant temperature process. So let us take an example. Consider 1 mole of gas enclosed inside an isothermal container. P1, V1 and T are the initial variable pressure, temperature and volume, and that will be expanded up to final volume, pressure and temperature P2, V2 and T2. Sorry, here temperature remains constant. Both initial and final state, the temperature is remain constant, whereas pressure and volume can be changed from initial state to final state. So what will be the work done equation? So W is equal to integral PdV subject to V1 and V2, initial and final volume. So we know that PV equal to RT, the gas equation. So P is equal to RT by V. So substitute this value in the place of P inside the integration. So RT by V into dV, integral V1 and V2. Now bring the constant term outside the integral part. R and T are the constant. So remaining thing dV by V, that will be kept as such inside the integral. So now V1 and V2. Now integrate dV by V, RT into, that will be written as ln of V, substituting the upper limit and lower limit. So RT into ln of V2 minus V1. So bring the constant term outside ln. So we can rewrite as V2 by V1. RT into ln V2 by V. So this is the work done equation for isothermal process. The corresponding PV diagram is given here. So we can exchange the temperature, we can change the pressure and volume by maintaining the temperature as constant equilibrium. So it is an isothermal expansion. Next one, polytropic process. So PV power n equal to constant. This is the given equation expression for polytropic process, where n is the polytropic index that may vary from 0, 1, 2, 3, etc. So let us see the work done equation. W is equal to integral PdV subject to V1 and V2. So here we know PV power n equal to constant. So the above equation can be rewritten as P is equal to C by V power n. So substitute in place of P, C by V power n into dV. Now, further this can be rewritten as integral V1, V2, C into V power minus n into dV. So the denominator term, if you bring it to the numerator, so V power n will become V power minus n. Now CV into V power minus n into dV. CV power minus n into dV. So we have to integrate this given term with respect to V1 and V2. So CV power 1 minus n divided by 1 minus n. So substitute the upper and lower limit. So C into V2 1 power 1 minus n divided by 1 minus n minus C into V1 power 1 minus n by 1 minus n. Multiply through negative symbol the above equation or 10 equation, so that the minus sign will become positive and this term will become negative. So now replace CV power minus n with the P. So here, so instead of CV power minus n, so we can replace it with the pressure value P. So P equal to C into V power n. Okay. So P1 V1 minus P2 V2 by n minus 1. This is the final equation, work done equation for polytropic process. Last one is adiabatic process. So PV power gamma equal to constant. Gamma is equal to Cp by Cv. So substitute given work done equation, apply the adiabatic equation PV power gamma equal to constant and do the simplification process. And this is the final work done equation for the adiabatic process. Instead of n, here we need to put gamma for adiabatic process. Whereas in polytropic process, we have to substitute power n. So with this, I thank each and every one of you for your continuous support. So in the next class, we will see the remaining additional part in thermodynamics. So thank you one and all present here.